Welcome to The Explainer. Today, we are diving deep, really deep, into one of the biggest, most powerful machines on the entire planet, the two-stroke marine diesel engine. These are the hidden giants that literally power our global economy, pushing those massive cargo ships across the oceans.
All right, to even start to wrap our heads around this, let's just talk about scale. The engine we're looking at stands 42 feet tall. Just picture that. That's as tall as a four-story building. It's an absolute behemoth of mechanical engineering.
But here's the thing that's really kind of mind-bending. It's how slowly this giant operates. Your car engine might be screaming along at 3,000 RPM, right? Well, these engines, they run at this incredibly slow, steady pace. We're talking like 60 to 120 RPM. See, they're not built to be fast and furious. They're built to be relentless. They're built for immense, unstoppable power. So the big question is, how does this behemoth actually create all that incredible power? Well, it all boils down to this surprisingly simple and super efficient two-stroke cycle right at its core.
It's really like an elegant dance of power happening over and over. So in the first stroke, the power stroke, you have this huge combustion event that forces the piston down, and that's what turns the massive crankshaft. Then on the second stroke, the piston zips right back up, compressing all that fresh air. And when you squeeze air that much, it gets hot, like crazy hot, over 900 degrees Fahrenheit. Hot enough that you don't even need a spark plug. The fuel just ignites on its own for the next power stroke. So you get one full power cycle for every single revolution of that crankshaft. Super efficient. Okay, but to keep that cycle going again and again, the engine has to breathe, right? At the end of that power stroke, the cylinder's just full of hot exhaust. So this is where a really crucial step comes in. It's called scavenging. And it's basically where a huge blast of fresh, pressurized air comes in and literally shoves all the old, burnt gas out through the exhaust valve. Now, this isn't just some simple mechanical process. Think of it more like a complete life support system for this mechanical giant. So let's break down how it gets that fresh air and, maybe just as important, how it deals with the incredible heat it generates. So it all starts with the exhaust itself. Instead of just being wasted energy shot out into the atmosphere, that hot gas gets collected. It actually becomes a source of recycled power. From there, that hot, high-pressure exhaust is channeled straight into a turbocharger. And this is where it spins a turbine wheel at absolutely incredible speeds. This is where waste heat gets turned back into real, useful work. And see, that spinning turbine is connected to a compressor on the other side, which is just sucking in massive amounts of fresh air from the engine room and squeezing it down. But physics 101, right? When you compress air, it gets super hot. And that's not really what you want for efficient combustion. So, as the final step in this whole breathing process, that hot, compressed air gets pushed through an air cooler and then a mist catcher. This cools it right down, making it way denser, and it pulls out any water droplets. And what you're left with is the perfect charge of cool, dry, oxygen-packed air, all ready for that scavenging process we just talked about. Now, to handle all that insane internal heat, the engine has its own, really sophisticated circulatory system. There are these internal circuits of fresh water that are constantly flowing, absorbing heat from the cylinders. That super hot fresh water is then pumped through a heat exchanger, and this is where cold seawater, just drawn from right outside the ship, cools it down before it goes back into the engine. But, and this is the important part, the two water sources are kept completely separate. As the engineers say, they never, ever mix. Okay, so we've got all this power, all this breathing and cooling, but the crucial question is, how are all these powerful actions, like the fuel injection, the exhaust valves popping open, how is all that timed with, split-second precision? Well, the technology here has seen a massive evolution. For a really long time, and honestly on many ships still out on the ocean today, this was all controlled by a gigantic chain-driven camshaft. Think of this huge rotating shaft with these precisely shaped bumps or lobes on it that would physically, mechanically trigger everything at just the right moment. But, as you can imagine, modern engines now use an electronic control system, or ECS. It's all computers, giving them far more precise and way more efficient digital timing. But maybe the most surprising thing about these engines is how they go in reverse. Get this. There's no gearbox, there's no reverse gear. If you want to move the ship backward, the entire engine, all several thousand tons of it, has to grind to a complete stop. And then, huge blasts of starting air are shot into the cylinders in a totally different sequence to literally start the crankshaft spinning in the opposite direction. It's just wild.
All right, let's head deep inside the engine's structure now. Way down, beneath those massive cylinders, lies this absolutely cavernous space that's essential for both the engine's operation and its safety. We're talking about the crankcase. Inside this, well, this slippery oil-coated world, you've got the huge A-frames that basically form the engine's skeleton, and way at the bottom, the sump, where all the lubricating oil collects. And yeah, you heard that right. Crew members actually have to go inside this space for inspections. It's a very high-risk job, and it requires some incredibly intense safety procedures, as you can imagine.
And one of the most critical safety features down there are these things: explosion relief valves. See, the heat inside the crankcase can sometimes vaporize some of the lubricating oil, creating a potentially explosive atmosphere. These valves are designed to vent that pressure safely if it builds up. But, and this is the genius part, they're designed to snap shut immediately. Why? To prevent fresh air from the engine room from rushing in, because that could cause a much, much more dangerous secondary explosion. It's a really clever piece of safety engineering.
So, what exactly powers this whole incredible operation? And where in the world did this game-changing technology even come from? Let's start with its really unique fuel. The fuel for these giants is this thick, almost tar-like substance called heavy fuel oil, or HFO. It's basically a cheap byproduct from the oil refining process, but it is so thick, so dense, that it has to be heated by huge coils inside the fuel tank just so it can be pumped. Then it's heated again to an even higher temperature right before it can finally be sprayed into the cylinder as a fine mist. It's nasty stuff, but it's cheap and energy dense. And the engine's family tree is surprisingly direct. I mean, it all traces right back to the 1890s and the German inventor Rudolf Diesel. But it was these big engineering firms like Burmeister and Wayne, which is now part of a company called MAN Energy Solutions, that took his original concept and, over the next century, scaled it up into the absolute giants that power modern global shipping today. So, the power of this single machine, repeated on thousands and thousands of ships, is what physically moves our entire global economy. It's a true hidden giant, operating way out of sight on the high seas. And really, it leaves you with a final thought to ponder, doesn't it? What other incredible, unseen machines are out there, quietly keeping our world running?